Chapter 5, Unit 1. Today we're going to be talking about a Z-score, or what is referred to as a standard score. Basically, a Z-score simply tells you how many standard deviations you are above or below the mean. So look at the graph to the right, and everywhere we've had SD when we've made our table, we told how many standard deviations above or below the mean we are. Now we're just going to call this a Z-score. And again, we typically go from -3 all the way up to +3 when we're listing Z-scores. It's really just a new name for what you've already been doing. And we can easily transform any raw score, which is an X, into a Z-score. So for example, the table I gave you here shows IQ scores with a mean of 100 and a standard deviation of 15. That means we count by 15 to get to the next standard deviation. And it's very easy to use the Z-score to see where the raw score is located on the normal curve. Okay. And this will give us information about percent rank. You remember percentile rank? The higher the Z-score, the higher your percentage. Okay. So a person that has a percentile rank of 98% did much better than a person with a percentile rank of 50%, right? So we can do this, we can just compare Z-scores. So in this way we can say a Z-score of 2 is much better than a Z-score of 1. And a Z-score of 1 is much better than a Z-score of, say, -2.5. The higher your Z-score, the higher the original raw score. They're correlated together. So here's an example. We're going to use the same IQ. So I've already given you your table. So given an IQ score of 115, what is your percentile rank? Well, first we're going to convert to a Z-score. From the table we made, we can easily see that a score of 115 corresponds to a Z-score of +1. I'm going to draw my line at Z equals 1. And typically when we're talking about Z-scores, we would include 2 decimal places when we do our problems here, or when we report it in the literature. So I've drawn a line at Z equals 1. Now all I need to do is add up all the percentages to the left of that line. I can add them all up, 2.5 plus 13.5 plus 34 plus 34, or I can realize that half of that curve from the middle to the left is 50%. So if I can just start with 50% and then add 34% more, that gives me 84%. So if the student had an IQ of 115, they have a score higher than 84% of the population. And what I also want you to know is that the entire curve is 100%. So this means that if we subtract off that 84% where the student is at from 100%, that gives you 16%. That means that 16% of the population had a higher score than 115. So let's look at a second Z-score example. Given a population that has a mean of 120 and a standard deviation of 20, what's the percentile rank for a score of X equals 80? So what you want to do first is fill out your table. So again, Z-scores go from -3 to +3, and we know that the mean of 120 should be placed right at the Z-score equal to 0. And then with the standard deviation of 20, we're just counting by 20s to get to the next one. So if we start at 120 and add 20, we get 140. That's equal to a Z-score of 1. 160 equals a Z-score of 2, so forth and so on. Go ahead and fill out your chart. Then the next step, we convert our raw score to a Z-score. Just by looking at the table, we can see that a raw score of 80 will give us a Z-score of -2. So I draw my line at Z equals -2. And then I add up the percentages to the left of the line. So I can see if a student had a score of 80, they have a score higher than 2.5% of the population. Or in other words, 97.5% of the population had a better score than they did. Okay? All right, let's talk about comparing different standard deviations. So here I'm giving you pictures for 2 different distributions of exam scores. For both distributions, the mean is 20. But for the first distribution, the standard deviation is 2. And for the second distribution, the standard deviation is 10. and you made a score of 26 on both of these exams. Let's examine this a little closer. Let's see how our score of 26 compares for each distribution. I'm giving you a little bit clearer picture of the normal curve with 2 decimal places involved. So these are a little more accurate than what you normally see. I wanted you to be able to kind of see where the numbers are coming from. This is more accurate. So let's look at distribution 1. We have a score of 26. And so we're going to make a number line below our normal curve here. I'm going to call it x1. And below the z-scores, I'm going to put the regular scores. So we know the mean is 20. So for x1, I'm going to put 20 down that corresponds with a z-score of 0. And then I'm going to count by 2's because my standard deviation is 2. So I get 22, 24, 26. Going the other way, 18, 16, and 14. So go ahead and fill out your table for the first distribution. Okay? So once that table's complete, you can look at it and you can see that a score of 26 gives a z-score of 3. So go ahead and draw your line at z-score of 3. And then if you added up all the percentages to the left, you would get 99.87%. So you did really, really good on that exam. Only 0.14% of students did better than you. All right, let's look at the second distribution. So you're going to fill out your number line again, only this time you had a standard deviation of 10. So you're going to start with the mean of 20 that goes right below a z-score of 0, and this time you're going to count by tens. So you're going to put 30, 40, 50, and then you're going to go backwards, 10, 0, negative 10 on your number line. Does everybody see how this is made? So now we can see where a score of 26 is on this new number line. Well, it's halfway between a z-score of 0 and 1. So you're going to draw a line somewhere in there. And so your percentile rank is probably around, well, you know, the first half of the curve is 50%, and then you're kind of in the middle of the second one. So I'd say instead of the full 34%, I might guess it's around 20% of that 34%. So I might say that we're at about 70% would be your score on this particular test. So if you're comparing distribution 1 versus distribution 2, your score of 26 gave you a much better score on the first test at 99.87% than it did on the second test, where you only made a 70%. So in this chapter, we're going to learn how to calculate an exact z-score. So for distribution 2, we'd be able to find the exact z-score, whatever decimal point that is, somewhere between 0 and 1, and then we'd be able to look at a table to determine the exact percentage on the normal curve where we're at. So instead of having to guess that we're at 70%, we'd be able to look it up and tell exactly where we would be. So there's 2 main purposes for z-scores. The first one is each z-score tells the exact location of the original x value within the distribution. And then the z-scores from a standardized distribution can be directly compared to other distributions that have also been transformed into z-scores. So transforming 2 different sets of zeta into z-scores makes it so much easier to compare.